Hi, so welcome back to PH2011. Um, Based on input from students during our sort of open office hour, there was one topic that I wanted to post a little bit more about. It's less a topic of a particular chapter. It's not like a particular kind of problem that we solved or something like that. It's more um, a theme. So a student asked about calculus with regards to energy conservation, and it occurred to me that it might be a good idea to just kind of catalog all the appearances of calc in our class. So as we've talked about before, I mean, calculus is very much the language of physics. So it's nice to kind of see the different places that it has appeared, and I figured this might be a useful resource for you and helpful as you're studying for the final. It might give you a sense of the different kinds of places where you encounter calculus. So um, the answer to this question, where has calculus appeared, it has really been there with us from the beginning. So basically, the first thing that we talked about was kinematics. Um, and this was, way back in like chapter 2. And an application of calculus was we came up with some formulas, some algebraic expressions, assuming constant acceleration. So now, in general, the connection between acceleration and velocity was that velocity is the integral of acceleration. So if we imagine, if our acceleration is changing in time, as if it's a function of time, if you wanted to find the velocity, you'd have to integrate the acceleration. Now, if our acceleration is a constant, then this becomes just a. And a notable example is being g, the acceleration due to gravity near the surface of the Earth. So if your acceleration is constant, the integral of a constant is super easy. We just pick up a factor of t. And if this, as it's written, an indefinite integral, there would also be a constant here. Now, this constant is in this, in this situation, it has meaning. This would be the initial velocity. So this c is v naught. So what this amounts to is using integration to come up with one of our kinematics expressions. Basically, if we integrate a constant acceleration, we get that the velocity is the initial velocity plus the acceleration times time. Now we can do this again too. The displacement is going to be the integral of the velocity. Now, if our velocity is given by this, when you integrate this, what are you going to get? Well, you would pick up a factor of t on v naught. You'd pick up, this would become at squared over 2 and plus a constant. Now, in this case, the constant is the initial position. So, in other words, c would be x naught. And so if we put these pieces together, we can reorder them so that it looks more familiar. We have our other very useful, or another of our very useful kinematics expressions from integrating the velocity, assuming constant acceleration. And we can go the other way as well. So looking at the complementarity of calculus, Another way of stating this would be to say, okay, the velocity is the derivative of the position. So if we take a time derivative of our expression, it will undo the integration. And we'll recover. So x naught is a constant. Derivative will be 0. V naught t, we would have just V naught. 1/2 at squared, we would get, 1/2 times a times t times 2. So in other words, this would become at. And we've recovered our velocity expression, that velocity is V naught plus at. And if we were to do this again, noting that the acceleration is the time derivative of not position but velocity, you know that these are complementary. If we do that again, we recover the only thing that's gonna stay. So our v naught is a constant, that'll go away, and we would find that we recover the acceleration again. So that was kind of the first place that we encountered calculus. We can express these. We can convert between some of these kinematic expressions by noting that the relationships between acceleration, velocity, displacement, they're all connected, and we can connect them through calculus. So the next place that we ran into calculus was with regards to work. So calc appeared with regards to work. So work was chapter 7. And specifically, so recall, work was F dot D. And when F is not a constant, if you think about it, if it's as, instead of a constant, if it's a function of x, for example, then this work being f dot d becomes an integral, where work is the integral of the force dot some differential length. So it's looking at the dot product between the force as, actually, let me write this as f of x. Wow. It's depending on something. It depends on what coordinate system you're working in, but in practice, we usually talked about systems where, actually always, we looked at situations where f and d were parallel. So in other words, this f dot dl would just become, for example, f of x dx. So this was just to make it a little easier on ourselves, so we're not dealing with both the dot product and the integration at the same time. And the best example that we had with this was the spring. So the student asked about springs during review. This is an opportunity we can talk about finding the work done by a spring. So our cartoon for a spring, we have like a mass and a spring, and we can imagine compressing the spring some distance, or a displacement vector like that. Now the spring, recall the spring force, negative kx. The spring is going to push back with a force. It's pushing back, i.e. the spring force is negative. It's always opposing what you're trying to do to it. So, and this would be, of course, this is in compression. You can see the same thing if you stretch a spring. It would just flip our directions here. And the math is the same. Then it's still being negative, meaning that it's resisting the motion as you try and push on it. Now, the work in this case, we would integrate our force. Oh, sorry. Our spring force. So what is the spring force? This would be the integral of negative kx. And we could say that we moved this from x to, well, actually, let me put it like this. Let's say that we move this thing from x naught to x final. So remember, we can set the equilibrium position to be. We'll have the upper bound on our integration being x final, just to distinguish it from x, little x, the variable in integration. So when we integrate this, it's a simple integral, right? X, we would get x squared over 2. Evaluated from equilibrium to x final. This would become negative kx final squared over 2. This is the work done by the spring. And this work is negative because the spring and, or I should say the force of the spring and the displacement vector are not perpendicular, they're anti-parallel. You know, one is going like this, one is going like this, so it results in negative work. But we talked less about the work done by the spring and more about potential energy. So this gives us a connection to Chapter 8, potential energy. So this was kind of the next place that calculus appeared. So with regards to potential energy, in section 8.2, so this time-varying forces stuff, this was in section 7.3. And then we can connect this to potential energy, that's talked about in section 8.2, by noticing that the change in potential energy is equal to the negative work. And I should be careful here, work done by a conservative force. So in the context of our spring, what this means is that, so I'm just using PE to mean potential energy. Your book has it as U. They're the same thing here. So the potential energy in a spring would be the negative work done by the spring. So this would be negative kxf squared over 2. So in other words, the potential energy stored in a spring is k x squared over 2. So this gives us a connection to Chapter 8. And this also gives us an opportunity to demonstrate this complementary nature between integration and differentiation. So we've just used integration to say the following, that the potential is the negative integral of force. We're talking about conservative forces. Now, we can take a derivative. So suppose you want to know the force, and you start with a potential and you want to know the force. You can take a derivative on both sides of this. So let me actually, how do I want to write that? Let me just copy this statement. So we can take a derivative of both sides of this. Imagine I'm differentiating both sides. And so we would have that the derivative of the potential so if we take a derivative of an integral, those are going to cancel themselves. The differentiation is going to undo the integration. And so we would have negative fx. Now normally we write this as put the negative on the potential. Long story short, I'm not being very eloquent here, but just this complementarity between the force being the negative derivative of the potential and the potential being the negative integral of force. This is kind of neat. And it's a really, it's a really cool instance of calculus, this sort of, what do you call it? Like the fundamental theorem of calculus appearing in a physics context with regards to potentials and force. So that was in Chapter 8. And one place where we worked with this, one example of this, was gravity. So recall, we had two different formulations of gravity. When we're talking about the gravity basically of like satellites where r changes a lot, remember that the force of gravity in that situation was given by big G m over r squared, and really it has it's in the r hat direction. This is negative because it's an attractive force. So what we can do is we have this force expression. We can use our potential, so we can take the negative integral of this to find the potential. So the potential energy due to gravity is going to equal the negative integral of this thing. Now, what this is going to do is our differential length and the unit vector r is going to pick only the part of this that is changing in r. So in other words, this becomes, we can cancel our negative sign. This becomes an integral dr. R.dl will give you dr. So now we have something that's purely in the radial coordinate. If I can draw it, r. And so we can integrate this. We can pull out our constants. So in other words, we have, r to the negative 2. So this will give us negative r to the negative 1. And this is an indefinite integral, so this will be plus c. Now we've been using the convention that, so just to kind of sketch it out for you, that the constant is 0. So what this means is that when you're far away, there is no potential energy because, or let me just write this clean down here. Potential energy due to gravity is gmm negative gmm over r. And we set the constant intentionally to 0. So what this amounts to is that when you get far away, the potential energy goes to 0. So as r gets large, gravitational potential energy goes to 0. So everything has negative gravitational potential energy in this formulation. And this allowed us to connect to things like the escape velocity, other topics, and it's just it's a cool application of this connection between the potential energy and the force. So we started with the force of gravity back in like chapter 6, and here we integrate it, and we can find the potential energy due to that force. So it's pretty neat. The last place that we talked explicitly about calculus was in chapter 9. So momentum conservation. So remember momentum, mass times velocity. And we talked about how when Newton first formulated his second law, it wasn't as F equals ma, it was that force is dp dt. So, and this is kind of interesting because this is a little bit more general way of describing this. So we know that the momentum is mass times velocity. So normally the mass would remain constant. This would become a derivative of constant times v, so it would become dv dt. And we all know, like we talked about at the beginning here, dv dt is acceleration. So in other words, we've recovered F equals ma. But this also allows for the possibility of mass changing in time, which is just a little more general. then F equals ma. And this is actually a requirement for explaining things like rocket propulsion. And so that's kind of the last place that calculus appeared. But I figured just having this little video sort of summarizing the places that we've encountered calculus might be useful to you. And a student had asked about it, so I decided to record and share it with everybody. So um, uh, have a good rest of your last week, and it was a pleasure working with y'all. And I hope that this is useful as you study. So have a good one.